Well, you know, okay.
Yeah. So hi everyone. Today we are very happy to have Professor Jérôme Faist from ETH to talk about the breakdown of topological quantization of quantum effect in a cavity. So Jérôme, please take your time. Yeah.
Well, thank you, G, and thank you for this invitation, and thank you for giving me this opportunity to discuss those results here. Before I start, I would like to first acknowledge the work of the people who did the work, and especially Felice Pugliese, who really was the, did the hard work of, continuing those measurements when we were not really sure where we're going. But also, he's finished now, graduated, and also the work of Joséphine Enkner, who really contributed a lot on the scaling, then Lorenzo Graziotto. And also this project really deserved a lot of credit to the growers, so Matthias Beck in our group, and of course the fantastic material also of Christian Reichel and Werner Beckscheider. And then also Giacomo Scalari in my group, who really pushed this from the beginning, and also acknowledging the crucial contribution of Cristiano Ciuti. And he gave us kind of the hint on how to understand those results. And I will sort of cite those things as I go. So, really just taking a few seconds to take a few step backs. What is vacuum? Well, of course, it's as it was understood initially, was a region of space where everything is removed. And, ancient Greeks, they debated whether vacuum actually existed. They were saying, well, nature abhors the vacuum. And then, of course, the real vacuum started when Torricelli and Pascal demonstrated that you could actually, pump out gas and get vacuum. The sound does not propagate in vacuum. And so the question was, since sound doesn't propagate, but light does, well, maybe there is something in there, a luminiferous ether, that actually carries the propagation of light. And that led to this, the most famous negative experiment probably of all physics, which is the Michelson-Morley experiment. Now, quantum mechanics really went completely changed again the picture, because in quantum mechanics, vacuum is not void. And you can see it as kind of the one manifestation of the uncertainty, but really what is always observed is that there are random fluctuations of the fields inside the vacuum. And indeed, the space is permeated by virtual particles that appear and disappear constantly. And especially, we will be interested in the electromagnetic field. And the electromagnetic field, as you know, has basically 0-point fluctuations, which we called the vacuum field fluctuations. And what we will be interested is how to understand the effect of those vacuum field fluctuations, and can we engineer them? Obviously, what makes this observation difficult is that, because of energy conservation, you cannot extract energy out of the vacuum. So obviously, you need to find other ways of seeing their effects. So it's known now for many, many years that there are effects that rely, or let's say that are manifestation of the vacuum field fluctuations, like spontaneous emission, the most famous being the Lamb shift, which is the shift of the energy levels in the hydrogen atom due to the interaction with vacuum fluctuation. And recently, there's been really an interest in trying to go a bit further in characterizing vacuum fluctuation by kind of direct measurement. As I said, you cannot use an energy detector to detect vacuum fluctuation, but what you can do is use a field measurement, because the field measurement will not try to extract vacuum energy out of the vacuum, and that can be done using nonlinear optics. And that was started, is something that was started by the group of Alfred Leitensdorfer, that showed that you can actually, they observed in a sense that the noise of the measurement of field using a electro-optic sampling was increased a bit by the presence of vacuum fluctuation. And we went further and started looking at the correlation vacuum fluctuation by probing them at different times and different places. Now, today, what I would like to concentrate more is on the use of cavities to engineer vacuum fluctuation. And again, here, Casimir showed really many years ago a striking effect, the so-called Casimir force, which is the attraction of two metallic plates when you bring them very close together. And you can interpret this attraction between the two metallic plates as having really removed vacuum fluctuation out of the space that separate the two plates, because they basically, the fluctuations do not fit inside. And then you have a larger density of electromagnetic energy outside than inside. And in this way, you create a force. And another, of course, seminal work was the one of Purcell, who showed that using cavities, you can actually enhance or, in the contrary, prevent spontaneous emission to occur if you basically, if you change the density of state of electromagnetic fields inside a cavity by playing on this cavity. And of course, now, let's say the interest is whether we can really use those cavities to modify the states of matter. And okay, this list is not really up to date, but really, I just wanted to show that there's really a lot of work, theory work that has been done, trying to predict whether one can actually affect a phase transition using vacuum fluctuation, and especially if you engineer them using cavities. Now, obviously, there's also a number of theoretical work that predict that nothing should happen, or actually nothing dramatic should happen, because there are the so-called no-go theorems. So obviously, our approach has been mostly experimental, trying to say, well, how can we try and probe those ideas in real experiments? And one of our focus has been, well, what can we see that vacuum fluctuations, for example, could affect transport of electrons? And one way to see it is to think, okay, let's imagine that I have a cavity, I have vacuum fluctuations inside, and now I have electrons. Can this random electromagnetic field affect the transport of electrons? Now, one difficulty is obviously that the strength of those vacuum fluctuations is much weaker than the strength of the field that controls the motion of the electron in the crystal. So it's a tiny effect. And also, for this reason, we thought, well, let's choose a system which is extremely well controlled. And for that, we chose the quantum Hall system. So why did we choose this quantum Hall system? It really comes from two different directions. On one hand, it is because we know that in this regime, we're able to couple very strongly electrons to a cavity. And that we've shown by basically doing this kind of spectroscopy measurement that I show on the right here, where we look at the transmission of a system as a function of magnetic field, and we see that we have created polaritons, and those polaritons basically are the manifestation of a very strong light matter coupling, and the splitting of these two branches tells you how strongly this matter interacts with the vacuum fluctuation inside your cavity. But also, and that of course is done by using electrons in a magnetic field, which is exactly an electron in a 2D gas, high mobility 2D gas, that are interacting with the magnetic field. This is of course exactly the system that you use to look at the quantum Hall effect. In addition, in this quantum Hall regime, you can both investigate single particle and composite fermions via the fraction of quantum Hall effect. Just before I continue, I just write to stress the fact, if you have questions, please interrupt me. It helps me also focus, and if there is something not clear, please don't hesitate to ask questions. So just a very quick reminder, what are we talking about in a system? We basically talking about electrons moving in a very clean system. And for that reason, you can think of those electrons making classically cyclotron orbits. And those cyclotron orbits also reflect the fact that these electrons populate so-called Landau levels, which are equidistant levels that arise when you quantize electrons in a perpendicular magnetic field in 2D. So this is a harmonic system, and the number of Landau levels that you fill depends on the magnetic field. Now, what is, of course, very important for us is that the last Landau level can interact very strongly with light. If you send light at this spacing, at this Landau level spacing, because there is a very strong cyclotron absorption if your photon comes and raises one electron from this last filled Landau level to the next empty Landau level. And that transition can be made to couple to a resonator, as you will see. Of course, the nice thing is that this cyclotron resonance energy changes linearly with the magnetic field. So you see that the physics we will be talking about occurs for magnetic fields at around a Tesla or a bit larger than that, and cyclotron frequencies, which are between half a terahertz to basically 1 terahertz. So it is, of course, higher than microwave, but you can really think of them as being basically high frequency microwave for all the things that we're going to be discussing today. So what are the measurements we do? Well, we do very standard Hall measurements. So we take the sample, we fashion it into a Hall bar, we provide contacts, we drive the current along the Hall bar, and we measure both the longitudinal and the transverse voltage as function of magnetic field. What do you expect in the quantum Hall? Well, as its name indicates, you have this striking effect that the transverse Hall resistance is quantized in unit, or rather the conductance is quantized in units of 2e squared over h, or e squared over h if you take spin resolved plateau, while the longitudinal resistance drops to 0. And this you can see as an effect of topological protection. The idea is simply that when I do have a 2D gas, well, the interior of this 2D gas under the magnetic field is an insulator, because the electrons are doing their closed orbits and they basically don't participate to the transport. Now, electrons which are close to an edge, they will be actually scattering, they will have these skipping orbits along the edge, and those skipping orbits are the ones that basically carry the current inside the quantum Hall system. Now, you could say, well, what happens if I have an impurity? Well, if you don't have too many impurities, nothing happens. Why? Because, as was stressed already by Buttigieg many years ago, that electron that does this skipping orbit can hit the impurity, go one round, and continue its skipping orbits along the edge of the sample. So now the question is, okay, what are we expecting from vacuum fluctuations in that type of sample? So first of all, of course, one thing is that naturally, if you want, this topological protection does not extend to vacuum fluctuation. And the reason is those typically have wavelength, which, the vacuum field extends over the whole 2D gas. It's not a localized thing. And in that sense, just from fundamental principle, the topological robustness is not immune to non-local perturbations. So what, of course, we wanted to do is to investigate that effect of vacuum fluctuation by enhancing them, by making them into a cavity. And that is basically the prototypical experiments that we will be doing. Think about in the center, in this 3D rendering of our experiments, in the center you have this, this whole bar. So we're circulating a DC current or low frequency AC current along there. And this whole bar is immersed into this patterned gold layer, which basically acts as a resonator at these frequencies of hundreds of gigahertz. Now, why is it a resonator? It's a resonator because you can think of that gap as behaving as a capacitor, and the current circulating around this feature here as creating the inductor. So it's an LC type of circuit that will have a resonance at this hundreds of gigahertz. It does not have a very high Q. You know, the quality factor we claim in our experiments, the quality factor of the resonators basically almost do not play a role. The reason is, if you think of a lampshade for the hydrogen atom, the lampshade will not be changed by having sharp or, you know, weak resonances, because it's an it's a non-resonant effect. We will be looking for non-resonant effect, and for that reason, we don't believe that the quality factor of the resonator plays a big role. Now, in those type of resonator, however, what we observe is a very strong light matter coupling. The reason being, the volume of the electromagnetic field inside the resonator is way below lambda over 2 cube. So what you have here in color plot is the is the field of the, let's say, is the vacuum fluctuation field in the ground resonance, the fundamental resonance. There are, of course, many other resonances at higher frequencies. And the strength of that field is given by this formula, square root of h bar omega. And then below, you have the volume of the cavity. And so by decreasing the volume of the cavity, we can increase the strength of the vacuum field. And the strength of the vacuum field enters in the Rabi coupling, the light matter Rabi coupling. So not only do we have large vacuum fields because we have small volumes, we have also large dipole matrix elements because we are dealing with excited lambda levels, which are very large, extended, and they couple very well to light. We basically have a collection of those electrons because we are talking about the population of the last excited lambda level that is inside the cavity, and of course, the electron charge. So as a result...
May I ask a question?
Yeah, of course.
Sorry. So I was wondering about the field about the value of the field. You're talking now that there is a sort of the average of the field is the value that you are giving, or the field fluctuations, like the variance.
No, this is the peak. It's root mean square value of the field, if you want. For the ground, let's say this is for the lowest frequency resonance.
Mm-hmm.
It's about 5 volt per meter. That's what we get.
Okay.
As I will discuss later, this field is not homogeneous. It has actually maxima close to the edge of the metal. And that plays a role, actually.
So this is the classical field, so the expectation value of the electric field, or the variance?
No, this is the variance. This is meant
variance.
Because it is a vacuum fluctuation. So
it's the variance. Okay, that's what I wanted to make sure.
Yeah,
okay.
Sorry.
Thank you.
Absolutely.
Thank you.
I should have wrote it correctly. Yeah, thanks.
Yeah, thanks.
So how do we know that we have coupled well the light and the matter in our structure? Is by doing basically spectroscopy. And when we do spectroscopy, what we see is that the matter excitation, which is our lambda level or cyclotron resonance excitation, anti-crosses with the cavity excitation, giving rise to those two polaritons, the upper and the lower polaritons that you see here. And those two polaritons are splitted by something like 30%, or I say the splitting is 2 times omega. Omega divided by the center frequency of the cavity is 0.3. So the light matter coupling, because of this collective enhancement, is actually strongly enhanced in those cavities. Now, looking again a bit more carefully at how the sample is made, and again, this is an important detail, the metal goes very close to the edge of the 2D gas. So what you see on the left is a cleave through one of the sample, false colored, and you see on the left that you have the ending of this metal plates, and in the center we have the 2D gas, which is etched where the current is flowing. And on the right-hand side, we see how we drive the current, and we measure both longitudinal and the transverse voltage using those voltage probes, which are inside the cavity, but where the contacts are outside the cavity. Now, again, is something that will play a role in the end. In false color, you see, again, the strength of the RMS value of the fluctuation field inside the cavity.
Sorry, can I ask one question? So in the plot, the the device has a length scale of 40 μm.
Yeah, the width is 40 micron and the length is about 140 or so.
So the magnetic field you use is roughly 10 Tesla or 9 Tesla?
You know, as I said, the important physics or the strongest effects are occurring at around 1 Tesla also. So the cyclotron orbit is significant there. It's like
so actually my question is, you earlier said the vacuum fluctuation is non-uniform and plays an important role. But I think it's important to know what length scale the cavity field is from. So compared to the LB, which is magnetic length, which is very small, my question is whether the vacuum fluctuation is uniform or not.
It is our estimate. Of course, it depends on the magnetic field, obviously, and it depends on the frequency. But our estimates is there probably be a factor of 10 only between the decay length of the, you see, the field, if you look carefully across here, has actually 2 maxima close to the edge of the metal. And the decay length of that field is about 1 micron or so. And let's say, depending on the magnetic field, we estimate that the cyclotron orbit is between 10 and 100 nanometers. It, of course, depends whether you're at low field or high field. And so it is not many order of magnitude. It's maybe 1, maximum 2 order of magnitude. And we believe that actually plays a very important role in the physics.
So you mean even on the length scale of magnetic length, the cavity is also not very uniform.
Exactly. We believe this is an important aspect that even on this length, you cannot think you cannot assume that the field is constant.
Okay.
And I will go back, when I show different data, which makes us think that is the important physics behind it. So, of course, what we expect without a cavity is, of course, as I said already, this, this confined plateau in the resistance and the zero longitudinal resistance. And now, of course, it is also what we observe when we put the sample, the reference sample, because we always, on the same piece of material, we always processed one part of the sample with a cavity and one part of the sample without the cavity. They are processed at the same time, they are cooled down at the same time, they are measured at the same time with the same current. This way we can really compare. So this is what we observe, and what we should be seeing is nice quantized plateau. And when we compare that with a sample with the cavity at 140 gigahertz, we see striking differences. And those striking differences, I plot them with an arrow, is the fact that for odd plateau, it's obvious that the conductance quantization is lost, both in the longitudinal resistance and also in the transverse resistance. And you see here, for example, for the n = 5, we now almost have a maximum of, it's as if we were still on the preceding plateau, and same thing on the n = 7. And so there's really a dramatic change of the conductance when you put the cavity, and you will see much less happens on the even plateau, although when you look at low field, the even plateau are also modified. You see that the quantization of the even plateau is also much worse. But surprisingly, when we go to high magnetic field and we look, for example, at those features that are fractional features, the fractional features are still there. They're not going down to 0 anymore, but they are still there. And if we zoom, if you want, at the low magnetic field value, we see that indeed, at around this 1 Tesla, we see this very dramatic change in the quantization of now not only the odd, but also the even plateau. And we completely lose the quantization. Now, the other important aspect is that when we look at very low magnetic field down to 0, both curves go to exactly the same resistance, which means that we seem not to have affected the mobility of the sample at DC mobility of the sample. So in a sense, what we are doing is something which is very dramatic especially for odd plateau, a bit less dramatic for the even plateau, and even less for the fractions, which is something that is certainly uncommon. So to make a long story.
Sorry, before you
yeah.
continue, may I ask a
Yeah,
question?
of course.
So with respect to your previous plot, if I would translate the cavity frequency into magnetic field, where would, for example, the cavity frequency?
Well, you actually even have I can show you, this is the plot, you see.
Mhm.
The anti-crossing region is around 0.4 Tesla. So in a sense, at 1 Tesla, I'm already off resonance.
Off resonance, okay, thank you.
So you have to think of all this physics as being basically off resonant, at least for the ground, the fundamental frequency. And of course, the cavities have higher order resonances.
Hi, Jamal, you mentioned
Sure.
the fractional filling. Do you have data in the plot about the 1/3 Laplace state?
On that sample, we cannot reach it with the magnetic field. Let's say you mean the 1/3, huh?
Yeah. So here you have a
5/3.
first lambda level field, 1/3.
The 1/3 would be really at 18 Tesla or so. So that we cannot reach with our setup. So I will show you new data where we go higher in magnetic field. And indeed, that would be definitely a very interesting region to look for physics. And we were hoping to do that much faster than we did, because we said, well, we just changed the magnet in the cryostat. Well, that took much more time and much more energy than we thought. Huh? So yeah. Those things I was hoping to get them earlier. But okay, we're back now, really back on track. So, okay, what is the assumption? And really, Cristiano Ciuti in Paris, he really came up with a very nice model. At least it is a conceptual way of thinking of the effect that fits a lot of what we observe. In his model, he started by assuming there is a certain degree of electronic disorder. And he also assumed that, of course, you have very strong light-matter coupling. So in other words, what he assumed is that he considered processes where you would raise the electron to the first, excited Landau level. At the same time you emit a photon, you reabsorb immediately that photon and you go down. So it is a process, it's the typical anti-resonant process where you have an A dagger, B dagger. And in the end, summing over all those terms, one really nice aspect is that summing over all those possible channels for going from one edge to the next edge, he recovers the global light matter coupling, this famous large omega R, which does not come because he started from a polariton basis, but it comes out by summing over all possible states. Let's say the reason that this process needs some disorder is that if it does not assume some disorder, nothing gives, if you want, any momentum to the electron. So the electron goes up and goes down, and that doesn't change. Now, one thing that he stressed, and I believe for us it is really the most important aspect, is that that process is also allowed if you assume that you have a strong gradient of electric field. So if you go beyond just the dipole approximation. In other words, where the momentum is given by the photon rather than being given by the disorder. And what we will be doing now is basically looking at how well we can fit, if you want, or how can we explain our result based on this understanding. Now, I just have to warn you that we do not have a numerical calculation that would compute this effect from from first principle, simply because numerically we're not able, at least Cristiano was not able to do it.
Excuse me, may I ask a question?
Sure.
So in this model, you're assuming that the cavity field is in its vacuum state?
Yeah.
Is there a stimulated version of this? So if I inject a field, do I get something like an AC
start?
Of
course, you would definitely have that. And it would add you a lot of terms. The thing is, of course, we're looking for, and then you would have resonant terms. The thing is, this process is completely non-resonant because we obviously are in vacuum. So we cannot, have a process where we sort of, we need to borrow the energy to go up and the photon and emit the photon at the same time. Huh?
Right, but so if you do have presence of some photons in this cavity already, what effect would it have on the Hall transport that you showed on the previous slide?
I would think it would simply enhance this whole effect. I think it will simply make it stronger. We did some of that. To be honest, and perhaps what we should do is sort of revisit those data that we did, where we were, we were basically illuminating the sample with a terahertz, a very weak terahertz source. But the problem is a bit that when you do that, of course, it's hard to have. First of all, what we really want to show is the effect of vacuum fluctuation, and so, of course, then you do everything. You close your, you try to be at the lowest possible temperature, close all the windows, and so. So it's a bit, it's a bit of a thing that we moved from those illumination experiments to the dark experiments, because we wanted to really show that we are dominated, that what we are seeing is dominated by vacuum fluctuations. But I suspect that basically what we would see are simply a stronger effect of the same kind. That's my,
Okay, and so that's very helpful. My last question is just, so has nobody observed these kind of real field induced modifications of Hall transport before? It's very interesting.
Not to our knowledge. Let's say, I think part of it is probably, what I suspect is some of those things had been seen and called by other names, or let's say attributed to other things. Because if you're not, as you will see, for us, it was really a really strong experimental work to prove that, we're dealing with vacuum fluctuation and not something else. And of course, since at this point, we remain a bit at the disappointing state where we just say, oh, we take a beautiful sample, has a fantastic mobility, and we can, guess what? We can destroy the quantum hole in it. It is, of course, the first step. We hope to go further and do also constructive things out of it. But, I think it is, of course, it is difficult in a sense to, it's easy, in other words, it's easy to simply discard those data as being, something went wrong in the sample, and say, well, that's it. So, yeah.
Jérôme, could I add, I think you are completely right. In other spectroscopies with light-induced phenomena, you see these transverse currents, and then the question is that you cannot link them to any quantum fluctuations or any interesting phenomena in the material. Then, just to ask Nicholas, it's being called with different names. It's on this high-order nonlinear spectroscopy in materials, and it's completely sort of, let's call it, irrelevant for this quantum Hall physics. Although some people want to connect them. Then.
Yeah. Thanks.
No, just a comment. Sorry.
Yeah, sure.
Yeah.
Okay.
Hi, Jamal. I have one question.
Sure.
So let me first summarize this mechanism, and you can tell me if I'm correct or not. So this mechanism is literally indeed coupling to counterpropagating edge of the quantum Hall sample.
Yes.
From either disorder or from the gradient of the vacuum fluctuation.
Yes.
So there is one way to test whether this is indeed the mechanism or not. I think naively you can take two devices, one with a longer, wider width, and another with a small width, and see whether the modification will depend on the width of the system. Basically, the width means the distance between two edges.
Yeah. So look, very good point. It is obviously. I mean, we tried, I will show at the end of my talk that we tried to do that. The problem being, when you do those experiments, you need to keep the effect of the vacuum field the same. Otherwise, of course, you're not doing it. And of course, as soon as you change the size of the sample, the size of the strength of the vacuum field and its distribution changes also.
Yes, of course.
Because you're changing the resonator. So we have, if you want, direct and indirect evidence for what we say. The direct evidence, we've done an experiment where we try to do a scaling. Look, maybe I go back to that when I explain.
Yeah, that's great.
Goes along in my talk. So that's
thank you.
Yeah. So now, okay, first thing, what does this model explain? First of all, it explains relatively easily why the effect is stronger in odd versus even plateau. And it's stronger odd plateau because the Zeeman splitting, which is the term that separates the Landau level that are with opposite spins, is much weaker than the Landau level spacing, which means that when the Fermi energy lies between two plateaux with opposite spins, it's of course much closer to the Landau level, and therefore the wave function, if you want, is more spread, and therefore they overlap more, and therefore you can more easily go from one edge to the next. That's one thing. The other thing, as I said, was the fact that this fraction, they kind of stay like that. Well, there are two effects, we believe, that explain this. First is the so-called Cohn's theorem, meaning that electromagnetic field will couple to the center of mass motion of this many-body effect. Now, of course, that is true only when we keep the dipole approximation. So, of course, if you have now strong field gradients, that will not be perfectly true. And so, Cohn's theorem tells that the cyclotron resonance frequency is not affected by electron-electron scattering. But also, one thing which, of course, is also important is that those fractions, in our case, appear at very large magnetic fields, at least at larger magnetic fields, that is 1 Tesla, where we see the strong effect. And at larger magnetic field, we have also much smaller cyclotron orbits, and therefore their overlap is smaller, and then it's much harder to go from one edge to the next. So are you checking the chat? Because I see there's something on the chat, but I don't open it at this point.
Yes, I can read the question in the chat. What apparatus is being used for this? Please describe the physics experiment demonstrating this effect of the cavity on the electron motion. Yeah, so who asked the question? Maybe you can unmute yourself and directly ask.
Sorry, I didn't understand fully the question.
Yeah. Or maybe we can just go ahead and
Okay,
end.
I mean, and don't hesitate to interrupt. It's actually
okay.
So again, this is a bit of an experimental thing, but for us was extremely important to prove experimentally that what we are doing makes sense. And in a sense, the ultimate test for me was, let's make a sample where we don't compare a sample with a cavity with a sample without a cavity, but we do an experiment where we do have a cavity, we modify that cavity without touching the sample, and we see that something is moving. And so we had this experiment where we did the cavity, as shown here, and then we are providing a plate, a conducting plate, that we bring in close distance from the 2D gas. And we do that at cryogenic temperatures using these microactuators. And this is now at something like a few 20 millikelvin or 10 millikelvin. And of course, there's an experimental challenge to make sure that that plate remains parallel to the sample. So we glue it with a little bit of water, distilled water, and then we glue this actuator on the back, and then we are sure that our sample is nicely parallel. And what do we expect to see as a modification? Well, initially, our intuition was kind of wrong. I mean, it was right, but let's say the effect was the opposite of what we thought. Because we thought, okay, what you do when you compute here is I plot the in-plane field and the normal field when we have no additional metal plate. And when we bring the tip, or let's say the metal plate close, what we're doing is we can think of adding parallel capacitors, and therefore you can think of stealing away the electric field, which is within the gap, to put it somewhere else. So naively, we thought, okay, that's going to make if we do that, we should recover the quantization and having something that now is better quantized than before. Well, courtesy of Corona, we had a number of weeks where the lab was very quiet, no one was entering. So we could do very systematic measurements, bring the plate close at 200 nanometers, measuring, removing it far away, 3 micron, remeasuring, doing that back and forth 60 times. So it's about, a month or 2 months of work, and averaging the traces. And what was extremely interesting is indeed we could see that there was a systematic change in both the longitudinal and the transverse resistance, especially on odd plateau. So here, an odd state, you see that there is an increase in the longitudinal resistance and a change in the transverse one when we basically bring the metallic plane closer to the sample. And this is basically seen, of course, the effect is stronger as we go at lower magnetic field, where, of course, the effect is, as we said, expected to be larger. It's also larger for outfilling factor. So I want to stress here, we have a system, no illumination. We're at super low temperature. This is done at 12 millikelvin. And we are moving a metallic plate in proximity of a conductor, and we see a change in the conductance, which cannot be asserted to a DC field because this thing is completely screened, everything is grounded, we don't see any change in density. So it is really, if you want, you can think of a Casimir-like transistor. You're moving something and you change the conductance because you've changed the electromagnetic boundaries. We also checked, and that is just new, we did that now. We also checked that, you could not explain this change, even if it was totally unlikely that you would change the temperature, because everything is, as I said, was, the thermometers were always consistently showing 12 millitesla. This is the base temperature of the cryostat. But we also said, well, let's do a little exercise and let's, take the trace that we observe, this change in conductance. And since we had done measurements as function of temperature, you could say, what is the difference in temperature that would explain the change in the maximum of the trace? And that gave us a change in temperature of about 60 millikelvin, which is, of course, much too large to be credible. But also what is important is that if we assume that change of temperature, the change of temperature, we still see that the change in conductance, the quantization is 0, while the same change in off-resonant, if you want, conductance changes also the conductance in the quantized plateau. So what I wanted to stress is that even qualitatively, the effect is not the same as the one of a change of temperature. So it has really a signature which is different. And we saw it also in the transverse conductance, which is changed. Now, the point is that, and the reason that we were kind of initially quite startled by those results is that they had kind of the wrong sign. We were sort of making the quantization worse by bringing the metal close, until we understood that actually what we are doing when we bring the metallic plate closer is we are increasing the field gradients, because the field now is, because all those metals very close to each other create very strong field gradients. And since we're increasing the field gradients, we believe that effect is basically stronger than just the increase of the decrease of the average field. Now, we did also a little attempt to do a quantitative model. We're not satisfied with that model, but I will still show it. And the idea is, of course, to go back to the Büttiger-Landauer picture. The first thing that you notice is you just assume that you're able to scatter. This is, of course, what happens in a perfect quantum Hall conductor. The current is carried by those edge states. They are never backscattered. And, as such, that explains easily why you have a zero longitudinal resistance and quantized transverse resistance. Now, of course, the problem is even in that model, if you scatter a bit of one to the next, you don't get really what we measure. So we needed to go one step further, and we basically used what was called this network model of the quantum Hall, which initially was not really meant to deal with what we have, but meant to explain what is the shape of the Hall conductance between two plateaus. And there the idea is, well, the model is like, they were simply assuming that the last Landau level would scatter inside the bulk, and all the other Landau level would propagate, unperturbed, which is not a bad assumption. And they also assumed that the amount of scattering was basically proportional to the classical resistance of that segment, meaning the ratio of the length to the width. And that, I believe, is where this model fails for us. But still, the nice thing is we could apply it and we could try to fit it. So our assumption is the following. We said, well, we imagine that this scattering effect is occurring only in the region where we have the vacuum fluctuations. Everywhere else, the sample is wonderfully quantized. So we don't have any scattering there. So we assume simply that each segment of that conductor had a little bit of scattering, and that scattering was controlled by just one parameter. The amount of scattering in each segment being determined in the end by this aspect ratio length over width. And if you do that, the first good news is if you take the transverse resistance and you say, okay, that transverse resistance is due to this scattering, how much is then if I assume I know the longitudinal resistance, how much should be the transverse resistance according to that model? Well, that's a red dot. So it's not too bad. I mean, we are really fitting those data quite well. So it means that there is a certain level of truth in that model. And what is also very nice is that that model allows us to now put a number and quantify the amount of scattering. And what is interesting is we can do that for all the plateaus on which we observe a deviation for the quantization. And what we observe is that this rho xx decreases basically exponentially the magnetic field. And even more, what is interesting is I told you that the effect was stronger for the odd state. And I told you that it's because the Zeeman splitting is smaller than the Landau level splitting. But what is very interesting is that the exponential decay of the scattering as function of magnetic field has the same exponent whether I look at odd and even state. And that is very comforting, because this is obviously not what you would see if you were just looking at, for example, the temperature activation. How much is that quantization destroyed by temperature? If you were to do that measurement, the activation energy that you would get for the odd state would be the Zeeman gap, whereas for the even state would be the Landau level gap. Now here, what we find is that for both those states, we find the same decay. And that actually means simply that what we basically have is the gap for the effect for both the odd and the even plateau is the same. It's given by the slack photon energy, because what we need is we need to deal with this anti-resonant process that brings the electron to the next Landau level, not the next level, the next Landau level. So it remains a cyclotron gap. So the last thing which I will come back to is the fact that this characteristic energy that we derive is order of this light matter coupling strength. It's not equal to it, but it's order. It's the same order magnitude. And I'll come back to that. And the reason we don't expect that to be an identity is because in the end, we expect that effect to take into account the coupling of the cavity to all to all resonances, or to all photonic resonances of the cavity, not just the ground one. So if you need to sum the effect over all these possible trajectories or possibilities. Now,
I have one question about the activation gap and this plot. So this plot is done at a fixed cavity frequency. Is that correct?
Yes, it is.
Yeah. So how, if you vary the cavity frequency, how will the scaling change?
Okay, that is exactly what I will answer soon. So we will do the experiment, and I will explain why it's difficult to just change the cavity frequency alone.
Okay. Yeah.
Pavel?
So usually you're in the intermediate or small magnetic region, so that the Zeeman gap is comparable to the cyclotron gap.
No. The Zeeman gap is always much smaller than the cyclotron gap, because the Zeeman, you see, the Zeeman splitting both grow with the magnetic field, but the magnetic moment of the Zeeman gap is always much smaller than the cyclotron one. I will just show some data where we varied the angle of the magnetic field, and that meant increasing the size of the Z-man gap compared to the Landau gap, but we cannot bring them to the same value.
Okay.
Yes, Pavel?
Sorry, could you give an some idea why the dependence should be exponential? Because if I look at the expressions for gamma, it looks like 1 over omega or something.
Yeah, excellent. So the reason that we think it's exponential and it makes sense is that what you expect is in the end to have the overlap between the wave functions of the two edges. And that if you want the size of that wave function in area is basically proportional to the LB squared. And the LB is dependent on the square root of B, and therefore you get, and that's why we like it also.
And then frequency gives you the kind of propagation length, and then you have exponential suppression because overlap is exponential.
Exactly.
Thank you.
Exactly. So it's this decay, right? You expect that, absolutely. So now, so two things that we tried still is to change independently the Z-man gap. And what we see here, I will go a bit quickly because it's not, we just show that when we increase the Z-man gap and keep the component of the field normal constant, then we improve the quantization as we would expect. And what we also showed is that when we decrease the coupling strength and move the edges of the metal further away from the edges of the 2D gas, we basically also decrease. There we decrease, initially we interpreted this data only as function of the light matter coupling is decreased, but if you think about those gradients, of course, the more the edge, the further away the edge is, the less field gradients do we have also. So that would explain also why we see a stronger dependence in, let's say, the coupling than what we would expect. And we would expect something that goes like the square of the normalized coupling, and here we see something that basically was much stronger, an effect which is much stronger than this one. And that again, to me, points towards the importance of those strong field gradients. Now, back to this question, how can we sort of try to be a bit more quantitative and try to really look at, can we look at the scaling of this effect? So, as I said, the exponential dependence is really one that we expect because of this overlap of the Landau level wave function that had this characteristic size of LB. And the problem is, okay, if we want, for example, and our approach was to say, well, can we show that this exponential decay scales like the coupling, the Rabi frequency? And of course, so how can you change the Rabi frequency, keeping everything else the same? And you want to change the Rabi frequency, but you want also to keep the shape of the resonator the same. You want to also keep the ratio of the Rabi frequency to the center frequency, the resonator frequency. That means the strength of those anti-resonant terms to be the same. So in the end, what you turned out, if you look at those characteristic numbers, what you need to do is to change everything linearly. That means if you increase the frequency by a factor of 2, you need to increase the density by a factor of 2. You need to decrease the width of the resonator bar by a factor of 2, and all the linear scaling of the resonator. Of course, what is nice is those metallic resonators, you can really scale them geometrically. So if you make them, a factor of A smaller, the frequency is factor A bigger, so larger. It's very simple in that sense. Huh? It's nice because it's just Maxwell's equation being linear with frequency. That's all, in a sense. And it's really like it behaves like a perfect metal. So we did indeed that scaling, and so we went from a 2D gas that had a sheet density of 210 to the 11 to a sheet density of 410 to the 11. And as such, we went from a width of 40 micron to a width of 20 micron and a cavity frequency from 140 gigahertz to basically almost twice, a bit more than twice, 300 gigahertz. And this is what happens when we do the same type of plot. We had two resonator, we called, one is this split ring resonance, and the other one is slot antenna, just a square aperture. And what we see is basically we go from this CSRR, which is really kind of the, it looks the same as that one, the 140 gigahertz I showed you before. If we look, we basically can fit decently well this exponential decay with something like 0.8 electron volt of decay, which, we go from 0.37 to 0.8, which is really, it scales for twice the Rabi frequency. It's basically the scaling we were expecting. Now, we believe that obviously the accuracy of the fit is hampered by the dispersion, and that means simply that our experiment still, if you want, does not, it's not totally completely scaled in that sense. And I think what happened, if you look here, you see that the largest value of rho that we had in this sample were 10 or so. Here, the largest value of rho is like 0.5. And the reason is we did not scale the size of we didn't reduce the size of the contacts. And I believe the main mistake was to neglect this effect of the size of the probes. And the size of the probes should have been scaled. And that I will come back to that because that's kind of my conclusion at this point. So we also wanted to go deeper in the fractions. So we took a sample which shows in principle in large areas, shows nice 5/2 quantization. And we looked at, at the same measurement, basically in this 5/2 sample. We also went a bit higher in magnetic field. And there we see qualitatively a bit the same thing, but the effect is much less dramatic. So here you see that even in that cavity sample, depending on which cavity we choose, we still have evidence a bit for the 5/2. And when we zoom to lower magnetic field, well, we start to see that indeed the odd plateaus, they start to disappear. But as I said, the effect is much weaker than we were seeing in this other sample. And the reason is that in our initial sample, we had probes that were only 10 micron wide, arriving to the whole bar, which means that it's exponentially much easier to tunnel across and basically have the two edge states talk to each other across that, that 10 micron. Here we went to 30 micron. The reason that we used 30 micron was that we followed the indications of our colleagues who have worked a lot about those fragile fractions. And the fragile fractions, they don't show up if you have very small and very narrow probes. So that's why we chose relatively wide probes. But I think in doing so, we are decreasing very strongly the effect. So it's a bit of a trade-off in that point. What also we saw, and this is still work in progress, we saw very strong modulation of the Shubnikov-de-Haas oscillations at, again, between the odd and even plateaus, asymmetrically, and that we don't have really a good, we don't have a good explanation for that effect. It's really kind of striking that at some point, the Shubnikov-de-Haas seems to disappear. Now, those are all, yeah, sure.
The disappearance of Shubnikov-de-Haas, it seems that there is also a very strong modulation. Is it the same even odd effect, or is it something different?
Well, it is. You see, it's a good question because it must be, and honestly, we have not. I just, asked the student to prepare those slides today, so it's a bit fresh if you want. So it is definitely. It's a question of we are going from an odd to an even, and I should really think which one is the odd and which one is the even. So it seems like, if the last plateau is an odd and we are going to the even, that is where we have the strong modulation of the Shubnikov-de-Haas. Whereas when we go, the last plateau was an even and we go to an odd, then things seem to be much easier, or much sort of simpler. And that means that if it means that here, if you want, when you start from an even, it means that you are in the large gap and you're going into the Landau level, which is above the large gap, whereas the other one, you're going in the Landau level, which is above the narrow gap. And that is really why those two things are asymmetric. So again, since basically at this point, our model only deals with, if you want, plateau, we don't deal with what is between the plateau. Of course, we don't have really a theory now to explain what is going on at this point here. And we need to think about it.
Thanks.
Yeah. And yeah, and of course, the most dramatic question remains a question at this point, is whether, what all that we've seen so far, we always interpret those results as simply the vacuum fluctuations providing a scattering. So they basically, violate, if you want, the topological protection of the two edges. So the two edges talk to each other, and they basically, you have kind of a leakage current, if you want, from one edge to the next. Now, this prediction of, some of you is that, well, there's actually a much more dramatic effect that should happen, is a complete renormalization of the quantum hole. And now what my understanding is that to observe that, at least when we looked at our initial data, we didn't find such effect so far. But my understanding is that, well, if you really want to observe this effect, you need to contact the sample inside the cavity, because otherwise the Laughlin argument of topological protection is going to save the quantization. So we have a sample. It's actually being cooled between yesterday and today, and we should be starting the measurement very soon. So the experimental answer on whether we see that or not, unfortunately, I cannot bring just now, but it's hopefully we can answer that question very soon. With that, I just would like to summarize the conclusions. So we have an effect due to vacuum field. It's really, I think, experimentally, we've really shown a number of proof and try to look at this in many different ways. This picture of anti-resonant process is compatible with experimental data. We're still a bit lacking a quantitative understanding of the effect. And I think what we basically, the two things that we are missing in the theory, if you want, is really a stronger understanding of those field gradients. How much should they be? And also, if you look at the literature on quantum hole, especially if you look at the literature of what happens when you're sort of going out of the quantum hole, there the percolation picture is really something that people seem to really like. And I think the way I qualitatively understand those results is that what we have is the vacuum field fluctuation basically creates percolating path, or let's say allows path to go in saddle points or across saddle points that should be normally forbidden. And now that explains also why the effect is much stronger as we make, for example, the probing voltage narrower, because obviously there we are destroying the we're bringing those edge states much closer together. I think the outlook is obviously, on one hand, checking whether indeed there's a renormalization of the quantum hole. And as I said, I really hope that we could bring that answer very soon. Also, I think it's an interesting, this moving tip experiment. We want to push it further and now put a resonator on top of the tip and do a quantitative mapping that allows us to really look at basically the effect, also by modifying now in a very systematic way the fields and the field gradients, and also look at very different samples. And with that, I would like to also thank my group who did the work, and you for listening, and I'm welcoming your question, further question on the topic. Thank you.
Yeah, so hi, Jamal. Can I ask one question? So you
Sure,
mentioned the scaling of rho XX with the scaling. Can you summarize what determines the slope? Can you summarize it again?
Okay, the slope to me tells you what is effectively the strength. It really tells you what is the strength of the interaction. And of course, you would say, well, the strength of the interaction in the end should be it should be the light matter coupling, the collective light matter coupling. But you don't know exactly how to weight this one, because the light matter coupling is, of course, that the one that you measure is the one for the ground frequency resonance of the resonator. Now, since it's an anti-resonant effect, you not only have to think of the coupling and the effect of the vacuum fluctuation for the ground frequency, but also all the excited frequencies of that resonators will play a role, and they will sum. They will know. I mean, I don't understand this. I don't think there should be any, interference effect between those different. They will simply add, and that's why I assume for any given geometry and any given strength, that I should simply find an energy which is proportional to the Rabi frequency. Now, quantitatively, I don't know exactly. I didn't work it out.
So this rules out the you mean the activation gap you mentioned, because of the spin out and even effect. If it's activation gap, you would expect one slope larger, one slope smaller.
Exactly. If you do the same, let's say, if now you don't use this, if you now take one, quantum Hall plateau, and you say, okay, let me look at the activation of that minimum of resistance as function of temperature, and I do that for even and odd plateau, I will find very different activation energies, of course, because there the relevant gap is, of course, where is the next state. Here, the relevant gap is where is my next Landau level.
Mm-hmm. Okay, thank you.
Yeah.
I just want to clarify on this plot what, for example, orange symbols and red symbols. What's the difference at the different points in the sample where it's measured?
Okay, so the square symbols are corresponding to you have always two sides of a resonator, and so you can choose to measure the resistance on one side or the other. So this is the meaning of VXX1 and VXX2. That means we've measured the resistance on one side or the other of the resonator. To be honest, I assume SCS is this is just one of the resonator that they use simply.
So is it reasonable to say then that the resistance is sort of inhomogeneous? I mean, how important is this inhomogeneity, do you think? Like that you measure different sides and you get different things?
Exactly. That's the thing. Do you mind if I just turn on my light? Because as you see, the night is coming here and then I'm getting in the dark. So I started feeling being, in a cave.
In a cave, no?
Just illuminated by my screen. So, look, that's exactly the point. That's why that's why I'm actually, talking about this percolation picture, because in a way, it's clear when we make two resonators that are nominally identical, we don't find the exact same resistance. We don't find the exact same traces. But what we find is, as I showed here, for example, those are two different resonators, and even a resonator made on a different sample, you find very similar exponentials. So that's why there is one aspect which I believe is just driven by the very shape of the very specific trace depends on the arrangement of the impurities in that very sample.
Mm-hmm.
But let's say that's because, in a sense, by nature you're probing the weakest link, so you're always sensitive in a sense to kind of a very specific arrangement of disorder. You can think of this sample as being we sort of a bit inadvertently, we made a very strong amplifier of vacuum fluctuation in a sense. Because seeing such a strong effect from vacuum fields is like a bit surprising and almost scary. And of course, it comes about because we made these relatively narrow voltage lines that basically made the system very sensitive to very weak effects. And that's the way I understand it. And seeing the effect really decreasing the strength as we made those voltage lines larger, just to me is the way I understand that physics.
So one can summarize that basically the exponential is sort of universal, but the prefactor is determined by the shortest path, which is determined by this one. Thank you.
Yeah, that's what I don't know, of course, whether Vasil is your first or Deepak, I don't know. Or maybe Deepak, you are the first one because you're top.
Hi, am I audible?
Yeah.
Yeah, a nice talk. Actually, I'm wondering about the split ring resonator you mentioned. So basically, what parameters of the resonator the experiment is sensitive? Like, is it the split gap or the arm length of the resonator?
Okay, so we basically, in this experiment, we actually changed. You see here, for example, that's an example of where we try to change the shape of the resonator to change the light matter coupling, keeping the same resonant frequency. So typically, of course, for any shape, as I said, you can change the resonant frequency by just scaling linearly the size of the resonator. Now, when you change the shape of the resonator, you can basically change a bit the strength of the field enhancement in the gap, more or less. That's basically what you can do by changing the shape of that resonator.
So these resonators are basically metallic, right? Or
yeah, just a metallic plate. It's a high conducting plate. That's all, with a hole.
Okay, fine. Fine. Thank you.
Yes, thanks a lot, Jérôme, for the great talk. And I wanted to ask, like maybe a couple of questions. But the first one is like the picture that you described about how to understand these results is like in terms essentially of photon-assisted scattering through the impurities and so on and so forth. But I thought that but the way you started in the beginning is, of course, that in order to know that you have strong light matter coupling, you need to see that you have polariton branches showing up in the experiment. While then the polariton picture completely sort of went away. So I'm a little bit struggling to sort of between these two pictures, trying to sort of bridge them, understand them, like where are the polaritons for the cavity modifications of the Hall transport? Are they necessary to understand them or no, really? Or is it just scattering that's happening?
I mean, I be honest with you, I don't have a full, I don't have the full theoretical understanding. What I just know, if you want, and as I mentioned, what I really liked was that when Cristiano computed the strength of the effect, he did not start in a polaritonic basis, but somehow the characteristic light matter coupling strength that came out is the one that defines the existence of the polaritons. So in a way, the polariton comes back from a back door, even though it's not there from the beginning. And that, in a sense, for me was kind of good news, because one of the, remember when we showed first these experiments on the Shubnikov-Haas, obviously and we tried to compare them with the theory, which was a polaritonic theory at that point. One of the criticism was, well, in transport, you get a bit what you want depending on the basis you choose. So that was Andy Miel who told us that, and I must say, well, maybe you're right. But so in a sense, I was rather relieved that he didn't have to assume first a polariton basis and then get the result.
I see.
Because for transport, as much as for optical experiments, the polaritonic basis is a natural one.
Exactly.
As much for transport, it's not the thing that people usually use,
And now my second question is, because of course the paper, your science paper, is about breakdown of topology. I mean, at which point this scattering mechanism somehow violates the Thouless theorem of topological protection? Do you have an understanding of that, or is it this is too theoretical way of thinking about things, let's say? Because the Thouless theorem tells you that G nodes can explain way better than me that you have a gap, your system will get a quantized Hall conductance. So
yeah, I think in
disorder usually weak disorder cannot get you out of this somehow. So
yeah, I think two age are mixed, so it's possible to get modification if two age are mixed.
Right. You see, I mean, of course, I tend to see that through my very, practically oriented experimentalist eyes, which is, the topological protection always hints as infinitely sized systems, and some thermodynamics limits. And here I'm dealing with a sample that has a finite size and actually taking advantage of the finite size, because I know that if I make that sample go to infinity in size, and I don't need to go very far to get that, the effect is going to go down to zero. The reason, obviously, we call that a violation of topological protection. It's a bit also, in that sense, you might say it's a misnomer, because say, well, it was, there was not, it's never supposed to be protected topologically for any finite size sample. But still, I believe that it's an important thing to keep in mind when thinking also about all those proposals of using topological protection for quantum information processing, because there also you have to think, especially I'm thinking about the nanowires type of experiments where you have all those gates that are all very nice antennas, and where you expect to have very strong vacuum fields. And there one should really think whether the topological gap that is proposed will be strong enough to protect against the decurrence you want to protect against. So it's, of course, it's a question of, at this point, it's purely a practical, at least the way I see it. Now, maybe there is something else behind it, but at that point, I'm just seeing it as a very practical question.
Yeah, so I have a comment added to the Vasilis question. So if you open Soros' paper, indeed, he talked about infinity size or close the boundary condition. There's explicitly no age on his setup. And he proved that quantization, Hall connectivity is quantized. But there is a caveat. His theory is valid only when there's no long-range correlation. So in other words, the green function as a function of distance decay exponentially. So now if you if Chuti's proposal makes sense, I think maybe it's interesting to see whether the cavity can induce a long-range correlation. This long-range correlation will couple to edges on the finite size, and also closed boundary condition will maybe fundamentally modify the Hall connectivity, because the Soros theorem breaks down if you have long-range correlation. That's my view. Yeah.
Thank you.
Yeah, I have a question. So in your talk, you have a fitting from the Landau some model to experimental data. So that model is a phenomenological model or a first principle microscopic model.
You mean, okay, let's say.
Yeah, you have a red data points and compare to your experiments.
You mean this one?
Yeah, yes,
okay.
Yeah, this one, yeah.
Okay, there what we did is the following. We basically, I forgot whether we fitted or we simply assumed the values. You see, the model that we have here has effectively, three parameters, which basically characterize, one characterizes the aspect ratio of the leads, one characterizes the aspect ratio of whatever is here, and one characterizes the aspect ratio of that. Now, those are basically three numbers. Once those three numbers are fixed, we basically have only one free parameter, and this is rho xx nu. So rho xx nu in that sense is fitted to the value of the longitudinal resistance.
Mhm.
And once you have it, of course, the transverse resistance is not anymore a free parameter.
So here, this model is a phenomenological model. There is no, so you assume that there's scattering, refraction rate and other rates, right?
Right.
So this is not directly related to if you have a long range hopping mediated by cavity or you have a disorder.
Absolutely. There is completely, the only thing there, I'm simply assuming that there is a scattering mechanism that I don't understand that basically perturbates my quantum hole in my resonator. That's the assumption.
So it can be, so for whatever scattering mechanism, as long as they give you this phenomenological model, you get this fitting. Okay.
Exactly.
Okay. So my question is, on the theory side, is there any microscopic calculation based on the Chutis model tells like compared to experiment?
I have to look because I think Cristiano published recently a paper where he actually went one step further, I think, in trying to, and to be honest, I should have looked at that one a bit more carefully. But still, I think what is very challenging is that to avoid to diagonalize a 80,000 electron type of state, you know.
Yes, of course. Yes, and also your Hilbert space is enlarged by the photon numbers, and it's a challenging problem. Yes.
Yeah, it's a challenging problem. So, yeah, that's why we were initially. I mean, that's why I tried to think, okay, can we try to look at the scaling as one way to look at the system? But we see it's very hard to make it in a way that really. But at least let's say it shows. I think it shows something about the you know, that whether we understand. I think it points towards where we should look for. I mean, I think.
Right. Yeah, I agree. The scaling is very interesting, and maybe this is the first place to look at.
Yeah, this is true. Okay. No, it's not a question. Now, Jérôme, that you are here, you should tell me when do you think we could arrange another visit to Hamburg, and then we can coordinate.
That's excellent. Are you there? No, because there's one date that stayed alive despite everything that happened. 1st of December.
Yes.
Okay, it's a deal.
Okay. It's only that I have a meeting for the presentation of the two directors, but will be online. But I will be here. Excellent.
I'll
or the day before, even better, because then I don't have.
But I'm teaching. That's the problem. You see, I have this big lecture this semester, and that's why I'm a bit constrained.
Okay, we keep it on online, and if not, we do it after.
No, but let me do that for the 1st of December, right?
Okay, good. Thank you.
Sure.
Yeah. Thank you very much for the wonderful talk. Do we have other questions?
Thanks a lot for the very nice questions and the interest, and hopefully we're going to get some fresh things out of our oven soon.
And we should keep you updated with all the new developments, because
yes, and I'm very